Live. We are live. Good. There we go. All right. So today what we're going to talk about is polynomials. It is 9/26/19. Can you guys see that? Okay, that's my pencil, not my pen. Who knows where my pen is? Probably dropped it somewhere. Okay. So objective. We're going to talk about polynomials. And the term polynomials means many. Poly means many. In Latin, poly means many. Many numbers, but our numbers are x's, so we're going to go many terms with whole number exponents. Okay. Example 1 is not a polynomial. It could be if we let our x's be whole numbers. It could be. But this is really an exponential function, right? So if we want to do an exponential, this is the power function, but this is really an exponential. And it's an exponential function because the exponent is my x. It's an exponential function because my exponent is my variable, my x, okay? So graph the power function. Well, it's really an exponential function. There's two ways to do it, and if you haven't discovered the table feature, I'm going to show you. The table feature is kind of cool. So if I go to y equals, and I put clear, and I go my 3 parentheses 2 to the power of x, okay? We can look at the graph. Let me get a decent window though. Yeah, that'll work. Make it 10 to, if I graph it, it looks something like that, okay? A lot of times kids have a real difficult time graphing these because points help, right?
Wouldn't it just be 6 to the power of?
No, don't do that. Remember our order of operations? So our order of operations say you have to be able to do your exponent first, but you can't. So you can't multiply the 3 and the 2. Don't multiply the 3 and 2 because you have to be able to do the exponent first. So one of the ways we can do a t-table is go to your table. You got a table function, right? The nice thing about the table function, do you want me to show the table function again?
Wait, yes, please.
Yes, so clear, quit.
How do you get to the table?
So you go, it's in blue. So go second table. And it gives you all of the x, y, all of the points, all the x values. You want me to show it again?
Yeah.
Okay, so see it's in blue. See the blue?
Oh.
You go second table. So the nice thing about the table is we can graph pretty easily because we can go backwards and get some more values if we want to, right? So if I wanted to graph this, one, 2, 3, 5, 6, -1, -2. And if I look at my features, if I go to 3, I'm at 24, 4, I'm at 48, right? So I'll probably make my graph go maybe at 10, 20, 30, 40, and 50, okay? And then I can get some points like -2 and 0.75. I'm barely going to see it. It's like right about there. -1 and 1.5, barely there. And a 0 and a 3, a 1 and a 6, a 2 and a 12, a 3 and a 24, a 4 and a 48. Okay, what do you know about the shape of that graph?
It's exponentially going up.
Yeah, it is exponentially going up, and looks something like this, okay? This is an exponential function. It's growing exponentially. Have you heard that term?
Yeah.
Something's growing exponentially. I don't know if you guys remember a long time ago, there used to be that commercial where this guy's on his phone in a pet shop, and he's on the phone on hold, the rabbits keep multiplying, right? So anyway, the joke used to be like, don't multiply like rabbits, right? So it's as easy as if 2. 2 squared is 4. 8. Let's go real quickly. 2, then 4, then 8, then 16, then 32, then 64, 128. See how it's getting big fast, right? Our current world population is in trouble because we're doing the same thing. I will say this, not as a political thing, but the vast majority of the problems that we have on this earth is this. We have too many people. Okay? It really is. That is really, but then how do you solve that problem? Anyway.
No, the purge. The purge. Come on.
Also, the
Okay.
I've never seen the Purge.
So, I have never seen The Purge.
You haven't watched
No.
a good movie? Let's watch it in
actually
this
good.
class.
It's
Purge
good.
for election year is
It's
the
so
best.
good. Yeah.
It's the best movie I've ever watched.
Yeah, it's so good.
All right,
I
anyway.
watched a lot of movies too. So
Bef-
I don't know.
now, before I move on, sorry, you guys are so, you guys are like squirrels. You guys are like, rabbit, squirrel. You guys are so distracted. Okay, so let me ask you an easy question. Easy question. Will this graph ever cross this line?
No.
No, it can't. It's like half of a half. Half of a half of a half. Half of a half of a half. Will it ever reach 0? No. So we get a horizontal asymptote. Okay? I'm going to draw what we call a horizontal asymptote. And all an asymptote is like a boundary line. We've seen that before, right? It's a boundary line. And the asymptote shows us that it's bound here. It will never cross this line. Graphs will never touch asymptotes, but they get closer and closer to it, okay? So my horizontal asymptote is at y equals 0. That's my horizontal asymptote, okay? It gets closer and closer to 0, but it will never get there. You have to get to infinity for it to cross. You can't get to infinity, it's never going to cross, okay? It's like half of a half, half of a half of a half, half of a half of a half of a half, right? You'll never get to 0, right?
That's annoying.
Yeah. Okay, now, f of 6 is just plug in 6. 3 times 2 to the 6th power. Do the exponent first, right? Do the exponent first. So you got to go 2 to the 6th power is 64. It's really 3 times 64. You get an answer of 192, which is on this graph, but we won't see it. It's 6 and 92, right? At 1, 2, 3, 4, 5, 6, 192,
It's
right?
on our little table.
And it's on our table too. Absolutely, you're totally right, Zoe. Now, f of negative 3 is going to be a 3 times 2 to the negative 3. That's the same thing as 3 times 1 over 2 cubed, and that's using negative exponents. I don't know if you remember that or not. Which is the same thing as 3/8. Okay? And that is also on your table, isn't it, Zoe? But you'll see a decimal representation for 3/8. So that makes sense. We go back 1, 2, 3, negative 3. It's a super small value, right? Okay. So hopefully this is easy, right? Ask me if you get stuck, okay?
Yes.
Yeah.
No, just kidding.
Okay.
That's easy.
It is easy. Now, end behavior is a little bit tricky on this one. As I go to positive infinity, as x goes to positive infinity, what's y doing?
It's going up.
Right, so y is going to positive infinity. Get that? Now, this is where it gets tricky because as x goes to negative infinity, what's y doing?
Positive.
Closer,
What's-
closer to 0, but it can't touch it.
Right, so y
really close.
approaches 0. As I get further and further and further along, what's the height of this? It's going to 0. Will it ever get to 0? No, not unless you get to infinity, which you can't get to infinity, okay? Okay. Does that help? That's end behavior. All right, now, let's move on to the next one. So the next one. Okay, this is a polynomial. Standard form, biggest exponent, down to the next. So we're going to rewrite this as p of x is equal to a negative 4x cubed plus 6x squared plus 5x minus 5, right? What's the degree? 3. What's the leading? coefficient, negative 4. Now, before we do anything, we don't need to graph it. I already know this. And I can graph it really sloppy, doesn't really matter. All I need is in behavior, so bear with me. And we can put on the calculator. Don't put on the calculator. So we know two things. If it's x cubed, right? You guys watching? If it's x cubed, it's got to be like this, correct? But this is a negative x cubed, so it's going to go like that. So we know that this one's going to look something like this. And we can put it on our calculator. We don't need to put it on our calculator because all we're looking at is end behavior. So as x approaches, if we take a look at it, so as x approaches positive infinity, what's y doing?
Y is approaching negative infinity.
Yes, it's going down, right? It's going down. As x is approaching negative infinity, what's y approaching? And we don't even need to graph it. We can graph it if you want to, if you're curious, but I don't need to graph it because I just know. So the degree tells us a lot, and the leading coefficient tells us the rest as far as the shape and where the graph goes, okay? All right, not bad? So, and you guys know this, we just have to put it together, right? You actually do know all this. So the next thing, 3. So if I take a look at the last graph, I just threw it up here. X-intercepts, that would be here, here, and here. And I just made a graph up, right? But how about this graph? By factoring, okay? How many answers will it have?
3.
Good, it will have 3, so we should get 3 zeros, right? Zeros, intercepts, yep. So let's set it equal to 0 because the height of these points, the y value, the height of these points are 0, correct? So if we want to find the x-intercepts, we set it equal to 0, and we factor, okay? So what do you see? Do you see anything?
Yes, common factor out an x.
Yes. X squared minus 2x minus 8. Good?
And then many equations.
Yes, well, let's factor
So
again.
X equals 0.
No, yes, but let's factor this one again. Yes, yes.
So x
Let's factor this one again.
minus
Yep. Minus what?
4 plus 2.
Okay, now many equations. Now many equations. X equals 0, x equals 4, and x equals negative 2, right? Because you're going to solve the many equations. Set that equal to 0, right? Plus 4, set that equals 0, minus 4. Now, what this tells me, because I know quite a bit, I know end behavior, so I know I've got a 0 here. 1, 2, 3, 4, right? And 1, 2. Now, this is actually pretty handy because remember, the SAT, there's problems that you cannot use a calculator, right? So here's what we know. I know this graph looks like this. Nope, I'm wrong. I'm wrong. It looks like this. Okay? What's that? Okay. Okay, how do I know the graph looks like this? Okay. How do I know the graph looks like this? We've got zeros at 0, negative 2, and 4,
and
right?
0 again, right? Just kidding. That's
Not yet,
wrong.
not yet, not yet. No, because we don't have a double 0. However, how do I know it goes off like this at the end?
Because it's
Positive. And it's a cube, so it's got to go like this. Cubes are like this, right? So if it's going off this way, then at the end it's got to go that way. And we can, again, put it in our calculator, but I know it's got that shape. It's got that shape, okay? All right, ready to turn the page? Okay, now, find a polynomial, degree 2, with y-intercepts of 0, negative 2, and passing through the point negative 3, 0, and 3, 0. Okay, so, if I think about it, to get this answer, if this is a 0, this answer had to have come from an x plus 3 mini equation. This answer had to come from this mini equation, right? A positive 3 had to have come from this mini equation, right?
So then we're unfactoring it?
Yeah, we are unfactoring it, yep. So this is an equation that would go through negative 3 and 3, correct?
Yeah.
But a lot of graphs can do that. So I'm just going to show you real quick. Okay, that'll work, right? That'll work, right? That'll work, right? Oh, that won't work. That'll work. So which one is it?
Any of
I
them.
don't know, we have to find A to find out.
Yes, and we've got a point that it's got to go through. So if it goes through -2, it's probably going to look like this, right? So let's find the value of A that forces it to go through the point -0, -2. So that's easy because that's an X and a Y value, right? So I've got a X and a Y value, so we're going to go -2 equals A times 0 plus 3 times a 0 minus 3, right? So we plug in the 0 for the X's. And we'll put in the -2 for the Y, and let's find the A that forces it to go through the point -2, 0, okay? So if I solve, I got a -2 equals a -9A. All right, -9, because I got my 3 times my -3, correct? Divide by -9. Yep, and I get 2/9 equals the value of A. You guys okay with the 2/9? So now my actual equation is Y equals 2/9 times my X plus 3 and my X minus 3, okay? This parabola will have intercepts at -3 and 3, right? Because I'm in many equations. And because of the 2/9, it will force it to go through 0, -2. Thumbs up on that one? Okay, example 5. We did this yesterday. And if you're absent, that's okay, we'll do it again. Okay? So, we're not going to actually make it. We're actually not going to make the paper. We're actually going to get the equations. So let's say that we do have a piece of paper that happens to be 20 centimeters by 30, right? I'm going to cut out a corner, an arbitrary corner, meaning it could be any size. So if I cut out a square corner, and to make a box, I better cut out the same size square corner here, and I better cut out the same size here, and the same size here, right? And Lana, you weren't here, but I think you guys did this in Claridge, okay? So if you cut out all those corners, you can build yourself a box without a lid, right? And we did that yesterday, right? In fact, I've got a whole bunch of them from yesterday. And we made, remember we made all these boxes yesterday, right? So we made the boxes yesterday, right? And if you weren't here, you missed out on box building.
We did that last semester, not this year.
In Claridge's, yeah. So now if we take a look at this, before we go any further, if I fold this, I say arbitrary size, so it could be any. Could be any. It could be a variable size, so let's call it X, because we don't know how big it is, right? And so then when I build my box, the height of the box is X. Can you see that, how this folds up?
Yes.
This length was 30, but I cut out the 2 pieces, so this side is no longer 30, but it's 30 minus 2x, right? That's going to be this length. This width, yeah, is no longer 20, but 20 minus 2x, yep, which is this length.
30 minus
Wait.
2x, and then 20 minus 2x.
So, how do we find volume?
Why is
Length.
it 2x? Wouldn't it be 4x?
No, because I'm just cutting away here and here, right?
But there's 4x's on that side.
You weren't here, but I'll do it real quick. You gotta take a box apart, okay? Sorry, whoever's box. Take apart this one, okay? Okay, so I cut away here and here only. I lost that and that. All the way across,
We
right?
also
I
lost
lost that
that
much and that much. Just on this side.
Okay,
Just on this side, I lost that and that.
okay.
So that's 2 x's.
Oh, I see, I see.
Okay, good. Okay, now, how do you find the volume of any box? Volume is X times 20 minus 2x times 30 minus 2x, right?
What does B mean?
Volume.
Volume. So the volume of this box is length times width times height, right? Length times width times height. And if I want to find the best box, I graph it. So let's graph this. So I got my y equals. I'm going to put it in my calculator. And I'm going to go x times 20 minus 2x and a 30 minus 2x. Put it on my calculator. Now before I hit graph, I got to think about my window, okay? I do know that the very biggest cut I can make is 10 and 10, right? 10 and 10, because if I cut 10 and 10, then the paper's gone, right? So the biggest cuts when I go to my window, right? My window, I'm going to make sure I go from 0 to 10, but I might go a little bit bigger than 10. But 0 to 10 will work, okay? My volume is going to be pretty big because I'm going to have at least 20 times 30 is 600, right? And it could be maybe even 10 here, right? So I'm thinking 6,000. Are you with me? How big my box could be? 20 times 10 is 600, could be another 10 here. So I'm going to go 6,000 on my Y max. So my Y max 6,000. And if I'm not quite big enough, I can adjust. So I graph it, okay? And I'm looking for the max, right? The max is there. So I can calculate my maximum. And I'm going to go over, left bound. So the calculator just needs to know where to look. Because some of these things can roll like this. And I might have lots of different maxes. You just have to tell it where to look. Enter max. If you had Desmos, we just find a point, right? But anyway, here. So we get our max at about 3.9. So we get a 3.9, comma, 1056. Okay, so 3.9 is the best cut to make the greatest volume, right? So this is my cut size, and that's my corresponding volume. Okay. And if you're here yesterday, it totally makes sense, right?
Yeah.
Totally. Okay.